Hi everyone, I hope you're all doing very well and studying for the exam, but I have received a ton of emails about MO theory and saying that they're having trouble basically mastering the concept with just an online course. So what I thought I'd do is just shoot a really quick video and kind of show you how I personally teach molecular orbital theory, and maybe that will help you prepare for the exam, maybe not. And please feel free to fast forward and skip through parts that are easy or too hard, or rewatch things that you want me to say again, like that's completely fine. But please know I am just shooting this to try to help you master the material a little bit. So let's just start from the very, very beginning. And anytime I like to teach molecular orbital theory, basically what I like to do is review what we're doing. And so basically whenever you talk about a molecular orbital theory, what you need to remember is that what you're doing is you're taking an atomic orbital. So this is an atomic orbital. And then you smash it together with a second atomic orbital. So that's what this one would be. Another atomic orbital. And what you do is when you combine the two together, when you take one atomic orbital and a second atomic orbital and you put them together and kind of marry them or create a relationship, in other words, you force them to hold hands. You force them to have some kind of overlap that allow for electrons to travel back and forth. And so when you do that, you end up creating what are called molecular orbitals. So molecular meaning you're doing this for an entire molecule. Atomic orbitals meaning you're just doing this for an atom. So the biggest difference between valence bond theory and molecular orbital theory is that molecular orbital theory is for the entire molecule. You basically take all the electrons, put them in a box, shake them up, and then redistribute them and try to figure out everything for the molecule. Whereas valence bond theory is very, very localized. You're looking at one specific atom within a molecule. Molecular orbital theory, very, very different. All right, so the second thing I like to point out when I teach molecular orbital theory is that you need to understand what your labels mean, because the labels are telling you a lot of information. So the first thing you need to know, if you ever see a single line like that or a single orbital, we're talking about a sigma bond, okay? So one thing means sigma, two means pi. So if you ever see two different orbitals, two degenerate orbitals, we're talking about a pi bond, so a double or a triple bond, okay? That's what you kind of need to be thinking. The second thing you need to be thinking about is what these stars mean, okay? So if you ever see something that's considered a bonding orbital, I'm going to put that in quotes. Bonding orbital means that you have something that is very, very stable, or it stabilizes your molecule. It is something that is lower in energy than the original atomic orbital, and therefore we mark it with no star. Okay, that's the most important thing, no star. Whereas if you have an anti-bonding orbital, anti-bonding means you're at higher energy. So instead of saying stable, I would actually say that this would make something less stable. So unstable, you would say that it's higher in energy than your original atomic orbital, and then you mark this one with a star. So instead of saying no star, we would definitely say with star for this one. So with a star, and the stars look just like that. Okay? And so we need to kind of keep this in the back of our mind as we go through the molecular orbital diagrams. What do these actually mean? What do these symbols mean? Because these labels tell us a lot of information about the molecular orbital. All right, the last thing I want to tell you is my personal approach of how I craft a molecular orbital. And so I have just kind of a list. There's 9 different steps, and this is the way I do it every single time. So the first thing I do is I draw my atomic orbitals. You have to draw your atomic orbitals. If you don't do that, you're not going to do this properly. That means you're just memorize something, and if you memorize something, you probably don't actually understand it. So draw your molecular orbitals, then you need to add your electrons. So draw your orbitals, then add your electrons to the atomic orbitals, AO, that's atomic orbitals. Third thing you need to do is adjust for charges. So what I mean there is if I ask you to draw something that is an overall positive or it's an overall negative, you need to adjust. So if it's a CO minus, that means you have an additional electron. So you need to add that electron in somewhere in your atomic orbital. Or if you have CO plus, that means it's positive. You have one less electron, so you need to remove an electron from your atomic orbitals. Number 4. You need to draw your molecular orbitals. So I'm just going to write MO, draw your molecular orbitals. Number 5. Add your electrons. Oh, excuse me, I skipped one. Assign your labels. Yes, that's correct. Assign your labels first. Number 6 is add your electrons. There we go. Add your electrons, and this would be to your molecular orbital. Number 7, I usually like to identify my HOMO and my LUMO. And number 8, I like to determine my bond order. So now remember, your bond order is BO, which is equal to your bonding orbitals minus your anti-bonding orbitals, and then you divide that by 2. Okay, so this is basically no star minus star divided by 2. Okay, so keep that in the back of your mind. And then the very last thing I like to do is assign my magnetism. So is something para or diamagnetic. Okay, so there's 9 different steps, and we're going to methodically work through a couple different examples to hopefully help you understand how to do this if you were to then ask me to do this on an exam or anything. So let's start off with the easiest example. This is the one we always start with, which is hydrogen. So the first thing you do is draw your atomic orbitals. So we're going to have a hydrogen here and a hydrogen here. For atomic orbitals for hydrogen, they each just have one very, very simple orbital. It's 1s. So we've drawn our atomic orbital. After we've done that, we need to add our electrons. Hydrogen only has 1 electron, so you just draw on your electrons. Perfect. Now we go to step 3. So now we start thinking about the overall molecule. Our overall molecule in this example is H2 with a neutral charge, so it's H2 raised to 0, not positive, not negative, so we don't have to do anything for step 3. Step 4, now we're drawing our molecular orbital diagram. So what you do is you start from your atomic orbitals, one needs to go below it and one needs to go above it. If you start with 2 atomic orbitals, you must end with 2 molecular orbitals. If you start with 4 atomic orbitals, you must end with 4 molecular orbitals. However many you start with, you must end with. If you somehow do have a different number, it will not work. So we have 1 right here, 1 right here, so we have 2 atomic orbitals total, so we need 2 molecular orbitals total. So I'm going to erase these arrows just because it's going to get clogged up, but hopefully you understand what I'm talking about. All right, so we've drawn our orbitals. Now what we have to do is assign our labels. So we label the ones that are in our molecular orbitals. So right here, this one at the bottom, it's a single line, so we're talking about a sigma orbital. Same thing above here, it's a single line, so that's sigma. The second thing you do is you label your subscript. So where did it actually come from? So in this example, it came from the 1s orbitals. Both of these molecular orbitals came from 1s, so both of them are going to have 1s and 1s. Now the last thing you have to do is identify the bonding. Is it bonding or anti-bonding? And the only way you do that is you look at your original energy. So the energy of these 1s orbitals is right here in the center. We see 1 is lower in energy, 1 molecular orbital is lower in energy, and 1 molecular orbital is higher in energy. So if you're higher in energy, that's considered anti-bonding. You are less stable. It's something that is not advantageous. So remember, the entire reason we're doing these molecular orbitals is we're trying to figure out if these things are going to bind together. Are these 2 atoms going to come together and form a molecule or not? And the way you do that is by crafting these molecular orbital diagrams and then figuring out the bond order and figuring out where these electrons actually arrive. So I want to remind you though, if your atomic orbitals start here, so this is the energy they start in, the only reason they're going to form a bond is if somehow when they come together, they're lower in energy. So they start here, atomic orbital, molecular orbital must be lower down here. If it's higher in energy, which an anti-bonding orbital is, that destabilizes your molecule, so it makes it less stable. There's less of a driving force for those 2 things to actually come together and form a bond. All right, so now we've labeled our pieces, so that's step 5. Now we can add our electrons. So now hydrogen, H2, is going to have 2 electrons, so 1 from the left side, 1 from the right side, 2 electrons total. So just like before when we were talking about electron configurations in the first bonding unit, or excuse me, the first unit we did, which was atomic theory, you start from the bottom and fill up. So we have 2 electrons, we put 2 in the bottom, done. We've added our electrons, nothing fancy. Now we get to calculate our HOMO and LUMO first, or determine our HOMO and LUMO. And so HOMO is your highest occupied molecular orbital. So that means the highest orbital that has electrons in it. So right here, that's our HOMO. Where your LUMO is your lowest unoccupied molecular orbital, meaning what is the orbital directly above the HOMO? The HOMO and LUMO are always right next to each other. You're never going to have a HOMO here and a LUMO here or a LUMO here. They're always right next to each other. HOMO is the one with the highest energy level orbital that has electrons. Your LUMO is the one directly above it that has no electrons in it, okay? All right, so we've assigned HOMO, we've assigned LUMO. Now we're going to calculate our bond order. So our bond order is simply our bonding orbitals minus our anti-bonding orbitals divided by 2. So no star minus star divided by 2. So right here, no star, we have 2 electrons in our HOMO in our bonding orbital. So we have 2 minus 0 electrons in our anti-bonding. So 2 minus 0 divided by 2 gives us an overall bond order of 1. So bond order of 1 just says that we're predicting that there is a single bond between the two hydrogen atoms. So you have a hydrogen here. Single bond means you're just predicting there's one single bond there, or they're sharing 2 electrons between the two. Very simple. That's what we're predicting, just a single bond. The last thing we want to do is identify the magnetic properties. So what we can see here is that there are 2 electrons that are paired together. So this is something that is definitely going to be considered diamagnetic. So what you're looking for when you look at magnetic properties is, are there any unpaired electrons? If there are any unpaired electrons, even if it's just one, that's going to be a paramagnetic species. But in this example, we have 0 unpaired electrons, so this is definitely diamagnetic. All right, let's move on to a harder one. How about He2, so helium-2. So first thing we do is draw our atomic orbitals. Here's one helium, here's another helium. Now they each have a 1s orbital, and they each have 2 electrons in it. So we draw our atomic orbitals, then we add our electrons. So now what we have to do is adjust for our charges. We're talking about our overall molecule is He2. There's no charge there, it's completely neutral, so we don't have to do anything for our charges to adjust for our species. Now we draw our molecular orbital diagram. So we have 2 orbitals total, 2 atomic orbitals, so we need 2 molecular orbitals. Boom and boom. One is lower, one is higher. Always the same. Now what we do is assign our labels. So it's a single line, a single orbital, so sigma, sigma. They each came from a 1s orbital. There's no other option here. And then your top one, your antibonding orbital, must have a star. Now we can fill our electrons. So we have 2 from the left atomic orbital, 2 from the right atomic orbital. 2 plus 2 gives us 4. So we have 1, 2, 3, and 4 electrons. So now what we can do is assign our HOMO and LUMO. HOMO is going to be your highest occupied molecular orbital, and so that's going to be your highest one here. We don't actually have a LUMO drawn in, so we can just draw it. Here's an orbital above it. This would be your LUMO. That's a very, very difficult question. We could never ask you that if I hadn't drawn something there. There's no way possible for you to know what that LUMO would be, but it must be the orbital that's directly above the highest one. Okay, so that's kind of a hard one. All right, so now what we can do is determine bond order. Bond order is bonding minus antibonding divided by 2. So bonding, I see 2 electrons right here. Antibonding, I see 2 electrons right there. So 2 minus 2 divided by 2 gives me 0. So what does that mean? If you get a bond order of 0, that means no bond. There's no driving force. There's no reason for 2 helium atoms to come together and form a bond. So what we're saying is if we have these 2 heliums, there's not going to be a bond. There's not going to be a double bond, not a triple bond. There's going to be 0 bonds between the two, meaning that these 2 things will not form a molecule. They would much rather stay as 2 atoms by themselves. Because look at this. If we were to remind ourselves that this is an energy scale, what we're saying is like this is at, let's just make up numbers, this is at 5 joules, whereas this is at 10 joules of energy. So it's significantly higher. They'd have to fight and have electrons at a much higher space than if they were just sitting there by themselves at their own without being a molecule. So there's 0 driving force for these 2 things to come together. That's what a bond order of 0 means. Now, let's pretend that we cared and we still wanted to keep going. If you find that there's 0, usually you don't want to keep doing analysis, but let's just say for this example that we do. And so what we see here is that every single electron is paired up, so this is definitely a diamagnetic species, okay? Hopefully this is making sense. I want to kind of plow forward here and move to a more complicated example, and so let's move to C2. All right, so we'll go through the steps here. C2, the first thing we do here is we draw out our atomic orbitals for carbon. So now that's going to be more complicated because now we have 2s and 2p. Now I'm choosing to ignore my 1s orbitals. That is very, very common. If it's something that's completely filled and you're looking at an inner shell, a lot of times people don't look at it. So you just want to use your orbitals for the valence shell. You can do it both ways. You'll always get the correct answer, but you need to be methodical. If you include your inner shell, there's more space for you to make a mistake, so just be really careful. All right, so atomic orbitals drawn. Now we need to add our electrons. Carbon has 4 valence electrons, so 1, 2, 3, 4. Same thing over here, 1, 2, 3, and 4. All right, so now adjust for our charge. C2 does not have a charge, so we don't have to do anything for that one, which is good. Now we need to draw our molecular orbitals. So this is where it gets a little bit more complicated. So we're going to start with our 2s. There are 2 2s orbitals, so we need 1 low one and 1 high one. Now we're going to focus on our 2p orbitals. So this is where you need to do memorization. If you are talking about an element that is boron, carbon, or nitrogen, okay, so boron, carbon, or nitrogen, the pattern's going to look like this. 2 on the bottom, then a single one, and then 2 on the bottom and a single one, okay? This part And this part is never going to change depending on what your element is. Okay, that's never going to change. The one part that will always change is right here. So this is where you need to do some memorization. Boron, carbon, nitrogen is going to have that part pattern. And I'll tell you what happens if you're looking at oxygen or fluorine in the future. But let me just get rid of that for now. All right, so this is our proper MO diagram. Now we need to do our labels. So this is a single orbital, so sigma, 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 sigma. But now we have two of them that have two orbitals. So this one's a pi and this one's a pi. Both orbitals are pi. Usually you just write one label instead of labeling each different orbital. So this is just how you would write it. All right, so now, where did these orbitals come from? So our first two sigmas came from the 2s orbitals. So that's where these are. And this one at the top is the highest energy, so that's going to be our antibonding. Now we move to our pi and sigma, pi and sigma. All 6 of these orbitals came from the 6 2p orbitals. So 2p, 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 and 2p. Now these top 3 up here, these are all our antibonding orbitals. They are the ones that are higher in energy than our original orbitals over here, so those have to be antibonding. All right, so now we can fill our electrons in. We have 4 valence electrons in each carbon atom, so 4 plus 4 gives us 8, so we can add these in from the bottom up. 1, 2, 3, 4, 5, 6, 7, and 8. So we're done right here. So now what we can do is identify HOMO and LUMO. We've got HOMO is right here. This is the one with electrons. The LUMO is the one directly above it. So our sigma 2p is the one that's going to be our LUMO. Sorry that I didn't leave enough space there. I feel bad about that. All right, so now what we need to do is write our bond order. Bonding minus antibonding. So the ones without stars minus stars. So 1, 2, 3, 4, 5, 6. Minus our antibonding, we only have 2 antibonding right here, so 6 minus 2 divided by 2. So 6 minus 2 is 4, 4 divided by 2 is 2, so we're predicting that a carbon-carbon molecule is going to have a double bond. So if we were to draw that out, it would be C double bond C. Now that's a really bizarre structure, obviously, but that's what our MO theory is predicting. Now the last thing we need to do is decide, is this going to be paramagnetic or diamagnetic? And so I look through every single electron in this molecular orbital diagram is paired up. So this is definitely something that is diamagnetic. Diamagnetic, okay? Let's do one more example, and hopefully this will help solidify this concept, our MO theory. But basically what you should be seeing is that this is the exact same thing over and over and over and over and over again. We just decide, or we just change everything up based on the number of electrons that we have. All right, so let's look at oxygen here, O2. First thing we do, write our atomic orbitals. So oxygen here, oxygen here. It's very similar to carbon. We have 2s and 2p. And just like with carbon, I'm ignoring the inner shell, so I'm completely ignoring the 1s electrons. Now, in like oxygen, for valence electrons, we have 6. So 1, 2, 3, 4, 5, and 6. Same thing over here. 1, 2, 3, 4, 5, and 6. Now we're talking about O2 neutral. We're not doing anything fancy here. I'm not going to put any charges on it, so we don't have to adjust for our charges. So we can just jump right into our next step, which is drawing our molecular orbital diagram. All right, so the first thing we have to do is figure out our 2s's. So there's 2 orbitals, so we need 2 things. So 1 on the bottom, 1 on the top. Then we have our 2p. Now this is the section. Remember this bottom section right here, these next 3 orbitals, that's what we have to memorize. If you have oxygen or fluorine or neon, so oxygen, fluorine, or neon, you do the one that has 1 and then 2. So the first one that we just did, or excuse me, the last one, which was C2, had 2 and then 1 for orbitals. For oxygen, fluorine, and neon, you flip those. So now you have 1 and then 2. The top part always looks like this, 2, 1, always. It never changes, all right? So now you go through and you write your labels. 1, so sigma, 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 there's 2 here, so that's pi, 2 here, there's pi, and then sigma. So now subscripts, where did this come from? The bottom 2 came from 2s, all top 6 came from our 2p, 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 2p. Now we have to do anti-bonding, so those are any orbitals that are higher in energy than they originated, so that we have 1, 2, 3, 4 of these in this example. Now we can fill in our electrons. So 6 plus 6 gives me 12 overall. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh, now we have unpaired electrons. Things are getting tricky here. All right, so now what we have to do is do our HOMO and LUMO. So our HOMO is going to be our highest one. That's right here. The LUMO is the one right above it because there's no electrons in there at all. Now the last thing we're going to do here is do our bond order. I guess we have 2 things left, bond order and magnetism. But bond order first, bonding minus antibonding. So for bonding, I see 1, 2 in our sigma 2s, then I'm going to jump right to our sigma 2p. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. We have 8. And then subtract out our antibonding. So 1, 2 here in our sigma 2s. Then I'm going to go up to the very top here to our pi 2p star. And so there's 2 right there. So we have 1, 2, 3, 4. So 8 minus 4 divided by 2, that number changes. 4 divided by 2 gives me 2 overall. So we're predicting a double bond, which should make sense if we're trying to predict what type of bonding structure would be between 2 oxygen atoms. And we absolutely should agree that a double bond would be what it would look like. The last thing we need to do is decide our magnetism properties, and so we can look through here. We see at the very, very top that we definitely have 2 electrons that are unpaired. So finally, we have an example of something that is considered paramagnetic. And so the only way we knew it was paramagnetic is because we were able to look right there at the top and see that there are unpaired electrons. If you have unpaired electrons, then you have a paramagnetic species. All right, that is everything I have for you today. Hopefully that makes just a little bit more sense. I'm just using this video as a way to supplement what we already have on the GChem website. I don't have time to go into this completely in depth as much as I'd want to on the review that we'll have on Wednesday, but I will be talking about everything else that's going to be on the exam. So good luck, take care of yourself, have a wonderful week, and if I don't see you, please have a very, very safe spring break.